ELISpot and FluoroSpot readers have always been complicated. XY table calibrations, subjective camera settings, and software that looks like it was made in the 1990s. Today we demonstrate something totally different: Mabtech Iris. Based on our raw spot technology, its accuracy in spot center detection in FluoroSpot analysis is truly remarkable. In this technical video tutorial, we will show you that and all the great features packed into this next generation ELISpot and FluoroSpot reader. We will together analyze two plates that have been done in parallel using the same isolated donor of PBMC, one infrared gamma ELISpot plate and a dual infrared gamma TNF FluoroSpot plate. A number of stimuli have been included, and we hope that you will get a good understanding of what Mabtech Iris has to offer your laboratory. Okay, we've now made it into the computer controlling our reader, and you might spot that we're currently using the macOS operating system. Yes, that's right people, Mabtech Iris is available for both Apple and Windows. We start off by double-clicking on the software icon from Mabtech Apex software. After logging in, we then click Open Workspace and are immediately prompted to select our assay principle. This part is naturally divided into either ELISpot or FluoroSpot. Are we going to be doing an experiment based on an MSIP white plate, clear plate, strip plate, or the special one without an underdrain called MIPS SW10? For FluoroSpot, you select if you're going to be doing single, dual, triple, or quad color FluoroSpot. The Mabtech Apex software is designed on the principle of being tab-based, just like any modern internet browser. That is, you can click on New Plate button and bring up several new at the same time, each selectable by its own tab. Let's for now take these tabs down and select ELISpot Clear Plate as our choice of analysis. We have now entered the main area of our software, and I just want to go over the basics. In the middle part, the 96-box well layout is naturally found and is flanked by different sections on either the right or the left-hand side. At the top, we have buttons corresponding to the major functions of the reader. I think most of these buttons should be pretty self-explanatory, and during the course of this technical tutorial, we will use many of them. The Save As functionality can be found under the File drop-down menu right up here. If we go down on the left side, we find the Information section, telling us what assay principle we are currently running, and a button for accessing the plate history. Here you can go back in time and see everything that has happened to your plate since it was created. Every change is documented. However, due to the way our raw spot technology works, the original raw data is never manipulated and is always accessible to all users that open up the plate, making the necessity of the history file less important. Below information, we have the View section where you find well selection and filter information. Furthest down, we have the layout system for adding your experimental setup. It is super easy to use, and we will totally revolutionize the amount of work you spend preparing your ELISpot data into graphs in Excel and GraphPad Prism. More on this later. On the right-hand side, we have the so-called presets. Here you control the spot counting threshold of our raw spot algorithm and the visual perception of the ELISpot wells. By default, there are 3 presets available that have different emphasis for counting ELISpot: normal, tiny, and big. We would recommend normal for an absolute majority of ELISpot experiments, but there are situations where the other 2 are better. You can click on the Show Preset button and get a visual overlay of which presets are currently applied to the 96-box layout. If you look carefully in the overlay image, you can see that the Mabtech default normal preset is applied to all 96 wells. Okay, we have now covered the basic structure of our software, and it's time to read our first ELISpot plate. We first select the wells we want to analyze and then hit Read. A red symbol appears in the top left corner and the XY table moves into position, and incoming raw images are captured and counted using our raw spot technology. Everything happens in one motion, both acquiring and counting. Another great aspect of the Mabtech Iris is that you never have to do any plate calibration prior to reading. This is done automatically for you upon startup. The XY table knows where it is, and there's no reason for us to waste our time manually calibrating it every time we restart the machine. Reading and counting is now done, and we can move the mouse and hover above the applied preset and click on the small Edit button. A pop-up window appears with all the settings that constitute a preset. Size and intensity are the threshold sliders for including or excluding detectable spots. Further down, the brightness and contrast sliders allow you to manipulate the visual representation of the raw images without affecting the spot count. Let me show you what happens when I move the sliders. Pretty cool, isn't it? By contrast, if we change the intensity and size sliders, spot counts immediately start changing. Here is another crazy good aspect of our FluoroSpot algorithm. Once you have counted a well, changing the sliders for size and intensity does not require you to do a recount. Spot counts are updated immediately without any delay. Finally, it's pretty cool to open up the preset and enter your analyte name, in this case interferon gamma. Doing so prompts the system to change the filter name accordingly, and this will be transferred into the Excel file once we save our plate. It is now time to access one of the wells and examine it a bit closer. We double-click and the software immediately launches a smaller so-called well tab for D3. Here, a large section is composed of the ELISpot image. To the right, we have the counted spots, the average spot diameter, and the average relative spot volume, all courtesy of our FluoroSpot technology algorithm. In addition, for spot diameter and relative spot volume, we have provided the minimum and maximum values as well. Below the well image, we have the preset controls for brightness, contrast, size and intensity, just as you saw earlier. To the right of the preset controls, we have something called max values. These are the recorded sensor values detected in our Sony sensor. Since our raw images are 12-bit, each pixel can vary in intensity between 0 and 4095. This ELISpot image have reached 3363 using our default exposure, and this is good, since it means that our sensor has not been saturated by the incoming signal generated by the ELISpot well. Since our algorithm is based on signals processing, we never wanted to hit the ceiling of the sensor. We will return to this topic in more detail when reading FluoroSpot. On the left side, we have a number of controls for edit mask and edit the area of interest. I will come back later to the masking functionality. Above, we have the layout section. Right now, we have not added any experimental setup to our plate reading, and as a result, all the circles are open, indicating that no data is available for viewing. I will later on return to the labeling system, as we also call it. In the view section, we have a number of switch buttons for turning on or off the visibility of data. We can also crop our ELISpot image and ask the software to show us the AOI. The zoom functionality allows you to zoom into the well and examine the spots more closely. Above view, we have the filter section, and above that, we have the orientation and information table. Here you can jump to any well you want in the plate, a very nice feature, but it also serves as a visual aid in identifying where you're currently located inside of the plate. Raw image information and count information are some basic data regarding the raw images that have been captured and counted. So what about the results? In well D3, we have incubated 250,000 PBMCs overnight in the presence of the KEF peptide pool. This PBMC donor have responded by having a significant number of CD8 positive T cells secrete interferon gamma during the 20-hour incubation. The 203 spots currently counted can be visualized by pressing the button here called interferon gamma. Red dots now show up in the well image, indicating the center point of the detected spots. The FluoroSpot algorithm has determined that the average relative spot volume of the 203 counted spot amount to 1.7 million. The spot with the maximum volume in this well is around 13.6 million. If someone were to ask me which spot this ought to be, my guess would be that it's this one. Let's find out. We bring up the spot centers again and just go in with the mouse and click on the red dot. Here we get the information of this particular spot, and yes, here is the confirmation. This is the spot with the highest detected volume in this well. The cell that generated this spot secreted the most amount of interferon gamma. FluoroSpot confirms my visual inspection. Although this demonstration by itself is pretty cool, we have to remember that there's a lack of dynamic range in ELISpot due to the chemical properties of substrate development. Bigger spots easily become saturated, meaning that volume values may become underestimated and skewed. This is a limitation that is overcome with FluoroSpot, and here the FluoroSpot algorithm really shines. Please stick around and we will come back to FluoroSpot later. If we now go back to the preset section below, I can change the size and intensity sliders just as I did previously. Increasing the intensity will make us count fewer but more intense spots. Likewise, increasing the size slider will make us count bigger and bigger spots. I can pull the size slider all the way up to 550-560. At this point, only one spot is still included, and it is the biggest one with the highest volume. I can also here in Well View change the brightness and contrast sliders. Again, this modification is only for my visual preference. It does not affect the spot count in any way. Let us now use the zoom function and go to 300%. I can now move around in the well using the Apple Touch mouse, a very nice experience. Here we can get a more detailed view of the spots and their corresponding spot centers as detected by FluoroSpot. Let us click on this smaller spot and then using the command key, click on this neighboring bigger spots. Two information windows now pop up and we can see that the volume values are drastically different. Around 300k versus 7.8 million, a factor of around 20. My guess is that in FluoroSpot we would have a difference of much more, since the signal and dynamic range is bigger and much more linear. Okay, we now close down the D3 Well tab and make it back to the unnamed Plate tab. It is time for us to save our plate. We hit save and the software asks us where we want to place our saved plate. I write in ELISpot Iris Plate 1. And let's place it right on the desktop. Saving the plate takes around 3 seconds and is indicated by the status bar up here. Let's go into the saved folder and check it out. The folder name is now ELISpot Iris Plate 1, just as we named it. Within it you can find an Excel file, a plate info file that should not be discarded, and 6 subfolders. The count folder contains count files we never interact with directly. These files are linked to each raw file using a hash-based verification system, whereby our software will instantly recognize if the high-resolution raw images or the count files have been edited or corrupted in any way. This functionality makes our saved folders impossible to manipulate without our software knowing it. Any attempt to do so will instantly be recognized by the Mabtech Apex software upon loading of the manipulated plate. Pretty clever programming. JPEG plate contains an overview of the entire plate, together with information on when it was read, when it was saved, and by which user. A lot of effort has gone into making the file small but still detailed enough so that you can actually judge the quality of the spots. JPEG Well contains JPEGs of all the wells captured. These look great and are rather small in size. They change in visual appearance depending on what setting you had on brightness and contrast upon saving your plate. Low resolution raw images is also pretty self-explanatory and forms the material for what we see in plate view. These are only visuals and never used for counting. Finally, we have a subfolder called Presets. Here you get a JPEG image showing what presets were used for reading our plate. If we zoom in, you will see that within the small overlay we can find all the information about how this plate was read by Iris. The size, intensity, brightness and contrast setting. 1603 pixels refers to the diameter of the AOI. We see the name of our preset and the name of our analyte. At the top, we are informed that exposure is the machine default for an MSIP clear ELISpot plate. One saved file I have not shown you yet is the Excel file. We have put a lot of effort into designing an Excel file that is smart and easy to understand. When opening up this Excel file, by default you always end up in the tab for spot forming units. But we also have tabs for general plate information about when the plate was read, when it was saved and by which user. Machine ID indicates the production number of the Iris machine that was used for reading it. We have used machine number 3 here at Mabtech. Furthermore, we have a separate tab called Plate Database. Here everything is saved pertaining to each analyzed well in the form of a database structure. This opens up for using pivot tables, but the real magic of this tab starts happening after we have added the experimental layout data. As a result, I will return later to this part of the Excel file in this tutorial. Furthermore, we have Average RSV tab, Average Spot Diameter tab, Layout tab, and an Exposure tab. Okay, let's close down the Excel file for now and let's move on. To fully understand Iris, we now have to return to the preset system. Up until this point, we have only used one preset for the entire plate. But what about situation where you want to use different settings for parts of the plate? For example, if you have analyzed interferon gamma in some wells and IL-2 in some others. You want to use different count settings but also different brightness settings for these two cytokines. No problem, we can just create more presets. Let me show you how to do it. We simply click on the Add Preset button. A clone of user-defined normal is created. I now go in and edit this preset by changing the name to Christian Favorite. I also change the color to blue. I then make some small adjustment to the analyte name and make some changes to the sliders. I then hit save and close. Okay, the preset has now been created, but I have not yet applied it to any wells. I do this easily by selecting a quadruplicate, right-clicking and then selecting Preset, Christian Favorite. Doing so immediately changes the spot count, brightness and contrast of the 4 selected wells. I can now confirm that my preset has been changed by pressing the button Show Preset, where I now clearly can see the blue Christian preset having been applied accordingly. If I now go in and edit this preset, changing the brightness, only these 4 wells are edited. If I double click on the well D7 and go into this tab, I can now change the preset here as well. Going back to the plate tab and pressing Show Presets now confirms that D7 is now also part of the Christian Favorite preset. I can now again select these 4 wells and go back to the original user-defined normal preset. You sometimes get dust and hairs into your ELISpot wells. These get counted by the algorithm. So how do you remove such artifacts? Well, we have decided to use a masking system. Engaging the Edit Mask in the Well tab allows you to draw away artifact spots, very similar to the Erase function in Photoshop. The smart thing about the masking system is that we never remove the original raw data, we only mask it. It is always possible to open up a saved plate, clear the edit mask and get back to the untouched raw data. For record keeping, if a mask has been applied, it gets indicated in Well View and Plate View by this editing symbol. In addition, if you resave the plate, a new subfolder is automatically created within the saved plate called Well Mask. Herein you can find a JPEG image that clearly shows where the mask has been applied. Furthermore, the plate database inside of the Excel file is also updated with the information that well C5 has been edited. It is now time to explain the layout system in Mabtech Iris. This is used for describing your ELISpot experiment and will reward you many times over by helping you to sort your data into GraphPad, Prism and Excel. You work in layers where each category can have as many labels as you want. You add a label by pressing the small plus sign. You delete a label by hovering with the mouse and pressing the trash can. A created label is opened by clicking on it. This brings up a menu where you can edit the name of the label and write in any kind of sub-information. You then tell the system to which wells in the 96 well plate this label should be added as metadata. You can multi-select the wells, and if you make a mistake, you press the small little cross over here to start over. You finish by clicking OK. Now the label is created. It goes from being an open circle to now being a closed circle. If you click with the mouse inside of the closed circle, an eye shows up, and a graphical representation of your label shows up among the 96 box layout. Very nice and very simple. We now move over to cells per well and create labels here as well. The first one is 50k for 50,000 PBMCs per well. This was the cell number for these 2 rows over here. We then use 250k for these, 400k for these. I now come to stimuli, and now you will fully understand the experimental setup of this infrared gamma ELISpot experiment. 6 different stimuli were used and an unstimulated control furthest to the left. We then had KEF in the row next to it. PPD at 400,000 cells per well were incubated here. TT for tetanus at 400k were next, and then Candida at 400k. We then used anti-CD3 and PHA as a positive control. With the stimuli layout out of the way, there's still one more category that needs to be filled out with labels. This one is extremely important if we want to analyze our data in Excel using pivot tables. The category is called replicate number, and with it I must describe how I used quadruplicates in this experiment. Therefore, I create 4 labels and name them 1, 2, 3 and 4. I can name them whatever, but they need to be in there. I then add them horizontally to my 96 well layout, indicating where I've had my quadruplicates, replicate 1, replicate 2, 3 and 4. I will show you later why this is so important for Excel. I have now finished my labeling, and I now can resave my plate again. If we now go into the saved folder of this plate, you will see that something has changed. First and foremost, a GraphPad Prism file has automatically been created. If we double-click on it and move it a little bit to the right, you will see what has happened. The Mabtech Apex software has taken our labels, sorted them into groups, and automatically pasted them into GraphPad Prism. I can now create a graph within Prism, tell it to use mean with range as error bars, and boom, the graph is ready. Let me zoom in a bit. I can now go in and edit the order of the columns. A pretty nice feature. We absolutely love GraphPad Prism at Mabtech. Let's go back to the resaved folder of this plate and check out this newly created subfolder called Experimental Setup. Here you can find 4 JPEGs, one for each layout category that I created before and used for labeling. Here you can get a graphical representation of your experimental setup, much nicer than if you were to do it yourself with pen and paper. Okay, after this we now go into the Excel file, and I will show you those replicates and why it's so magically important. If we now go into the plate database, you will see that all our labels have been added to their corresponding wells. Let us mark everything and insert a pivot table. Once here, you tell Excel that I want to use spot forming units for values after I've changed it to sum, and then for columns I want to use my replicate number layout information. I then add rows under the layout stimuli information. Boom! Here are my stimuli and my quadruplicates with their individual spot numbers lined up correctly. I can remove the grand totals. I can now make a graph with or without error bars. Very easy and very simple. Without the replicate information added in the layout system, you cannot get Excel to sort the data in this way. Having shown you the main benefits of what Mabtech Iris offers in terms of ELISpot, it is now time to read our Interferon Gamma TNF FluoroSpot plate. Remember, this plate has been run using the same donor PBMC and layout as our Interferon Gamma ELISpot plate we analyzed earlier. We simply bring up a new plate tab, change the filter configuration, mark our area, and then hit read. It is with FluoroSpot where the advantages of our raw spot technology really starts to shine. You see, FluoroSpot increases the complexity and demands put on readers, both in terms of hardware and software, since accurate identification of multiple secreting cells require that the true center points of the spots are correctly identified. Due to the diversity and intensity of cytokine secreting cells, doing this identification with the standard spot recognition algorithm using 8-bit images will always turn up suboptimal. You need to dig deeper and extract the full dynamic range of the signal offered through a 12-bit raw image, if you are to stand a chance of identifying the true center points in all spots. Furthermore, raw images are free of any user bias, since this image format represents the uncompressed, untouched electrical signals taken straight from the camera sensor. The capturing of ELISpot and FluoroSpot wells becomes objective and is not affected by camera settings like color, contrast, and digital gain. From a technological standpoint, RawSpot raises the bar tremendously, making FluoroSpot a much more robust and powerful immunological assay. With the reading finished, we now save the plate as FluoroSpot Iris Interferon Gamma TNF. Let us again place this folder right on the desktop. Functionality of our software when it comes to FluoroSpot is very similar to ELISpot. However, there are a few key differences. First off, we now have 2 filters selectable on the left-hand side, one for each lead and cytokine analyzed. As a result, we now also have 2 individual presets to adjust independently, one for each filter. The presets are only available for edit when only one filter is active, so let us uncheck the LED 640 filter in order to show us the LED 490 preset on the right-hand side. In ELISpot, we had presets with 3 different emphases, normal, tiny, and big. In FluoroSpot, there are no differences in emphasis, there is only one emphasis mode and preset to consider, which is of course nice. Let us open the LED 490 preset by clicking on the edit symbol and see what happens when we play with the brightness and contrast sliders. Again, these changes does not affect the spot count in any way, it is only for our visual preference. In addition, below contrast we have a slider called color tint. Here we can affect the amount of green luminance in our spots. If we pull the slider all the way to the right, the original raw image in black and white, as seen by our Sony sensor, can be visualized. I now add the correct analyte name to my LED 490 preset and make a small adjustment to the intensity slider. Spot counts update immediately. Okay, I think I'm pretty happy now with my interferon gamma settings. Let's switch over to the other LED 640 filter and let us open up the preset for TNF-alpha and play with the brightness and contrast settings in order to make the TNF-alpha spots look a bit clearer and nicer. Again, these modifications in brightness and contrast has no impact on my data, it's only the visuals. In addition, we should in the preset pop-up also edit the analyte name accordingly. This is more important in FluoroSpot than in ELISpot because it helps with the understanding of the cytokine secreting populations once in well view. But perhaps even more importantly, these analyte names are also transferred into the Excel file upon saving and will help quite a lot when making pivot tables. I will show you later on. We switch back to the interferon gamma filter and let us start off by first comparing the results between ELISpot and FluoroSpot in Mabtech Iris. For reference, I bring up the stimuli labels of the FluoroSpot plate. I have here taken the liberty of adding these labels prior to starting the screen recording, but let me explain something. You don't have to redo the label system every time you read a new plate. Simply bring up a previously saved plate with a desired layout design and use Save As. Okay, back to our result here. Let me switch back and forth between the interferon gamma result in this FluoroSpot plate and the interferon gamma ELISpot plate run in parallel using the same donor PBMC and experimental setup. As you can see, the consistency between the two methods is crazy good. Spot numbers of interferon gamma match up very well. Before, with previous readers, it was difficult to achieve the exact same sensitivity in ELISpot and FluoroSpot for all stimuli, but with Mabtech Iris, this changes. Let us now go into well C4 and check out the accuracy of spot center detection using our FluoroSpot algorithm. In this well, we have incubated 400,000 PBMCs together with PPD overnight. We first zoom in to 400%, but in order to see the spot centers in real detail, let me go even further to 800%. Here, the red dots indicates the center points of the spots. By lowering the brightness, we can confirm that the center points do in fact coincide with the peak signals generated by each spot. That is, the position of the cell that once gave rise to it during the incubation. Here, FluoroSpot provides a sort of accuracy and precision that we have been waiting for in order to take FluoroSpot analysis to the next level. It is so good at placing out the spot centers that it's truly remarkable and is a testament to the brilliance of the researchers at the Royal School of Technology in Stockholm who created this algorithm from scratch. Without the dynamic range of our FluoroSpot technology, this sort of evaluation cannot be done. Let us move to the other side of this well and let us find another typical example of how FluoroSpot enhances FluoroSpot analysis. With brightness high, it is impossible to see how this blob of spots could be 6 individual cells secreting interferon gamma. But now we're able to visually confirm this, that it's absolutely correct by just lowering the brightness. The first time I saw this, I was simply amazed. I instantly understood that this was the moment when FluoroSpot became the next generation assay we always knew it had the potential to be. Remember how we during the ELISpot section talked about the max values registered? I then told you that each 12-bit raw image had a range of 0 to 4095 and that we did not want to hit the ceiling of the sensor. However, in this FluoroSpot well, we have a max value of above 12,000 for interferon gamma. What is going on? Well, in order to extend our dynamic range in FluoroSpot, we utilize HDR, whereby we take 4 raw images in quick progression and smack them into one. This extends our sensor ceiling in FluoroSpot to 16,376 and allows us to set a rather low default exposure in the memory chip of each Mabtech Iris. This sets the foundation for how we are able to achieve a new level of plug and play. Nevertheless, you are of course given the possibility of overriding our exposure defaults in the preference section, and I will show you later on how to do that. But we do believe that our defaults will be good for an absolute majority of researchers. But keep in mind that by changing the defaults, you have to monitor these max values, making sure that you don't hit the ceiling of the sensor. We've now made it into the neighboring well C5 where 400,000 PBMCs were incubated together with tetanus. We can visualize this layout information by first clicking on the closed circles here in the layout section and then activating the switch button for show layout info, already done in the video. We then get a visual confirmation up here on the right hand side. Let us now dive in and talk a bit about the dual interferon gamma TNF FluoroSpot data and analyze its significance. First off, in well C5, IRIS has counted 71 interferon gamma spots, and the range of spot volume is from about 19,000 to 1.6 million, approximately a difference of 87x between the weakest and strongest spot. If we now look at TNF-alpha, we can see that IRIS has counted 876 spots in response to tetanus. By memory, I know that we had around 500 spots of background in the unstimulated controls, mainly due to monocytes secreting TNF-alpha. However, in this antigen-stimulated well, the larger spots are easily distinguishable and can be most likely attributed to antigen-specific T cells. IRIS is crazy good at separating large from small spots using the intensity threshold sliders, since the cutoff is done in the signaling domain. Furthermore, here a general benefit of FluoroSpot analysis compared to ELISpot becomes obvious. The interferon gamma secreting population of T cells is not the only one activated in a real antigen scenario. Other T cell populations may also be detected, in this case through TNF-alpha. A rather weak antigen-specific response can become very clear when including 2, 3 and 4 cytokines simultaneously in FluoroSpot. Among the TNF-alpha secreting cells, the spot with the largest volume is this one at 1,026,000. Let us go in and investigate that spot a bit closer. We first turn off the TNF-alpha dot indicators and instead ask the software to highlight the dual secreting population. Blue circles now highlight all TNF-alpha spots that have been determined to also secrete interferon gamma. Inside of each blue circle there are 2 small dots, indicating the center points of the interferon gamma spot in red and the TNF-alpha spot in green. Let me switch on the interferon gamma filter and then zoom in towards the biggest TNF-alpha spot in the entire well. At 1600% zoom, you can start to make out each individual pixel of our Sony sensor. The blue circles and the 2 dots are now clearly visible, and we can judge the distance between them at only around 1 pixel. Let us control how FluoroSpot has detected each center point. We first turn off the TNF-alpha filter and decrease brightness down. We then switch over and do the same for TNF. As you can see, the accuracy and precision of FluoroSpot is quite convincing. We're now back at 100%, and I just want to point out that the volume values detected in one filter cannot be compared with the volume values detected in another filter. However, very interesting comparisons can still be done between the different population subsets. For example, we can now ask the software again to visualize the population of 52 spots, both positive for interferon gamma and TNF-alpha, and let us look into the spot volume of this population compared to the single populations here. By changing the perspective, we can compare the average spot volumes for either interferon gamma or TNF-alpha. This opens up for very interesting data on unique cytokine signatures in the most immune-potent cells, the so-called polyfunctional T cells. Here, for example, we can see that the average production of interferon gamma in the dual population is rather similar to the single population. Nothing stands out. However, if we switch over to the TNF-alpha perspective using this drop-down menu, we can see how the dual population on average produces 328,000 of TNF-alpha, but only 56,000 in the single population, a rather significant 500% increase in cytokine output. Our experiment was run with quadruplicate wells, and we're currently standing in replicate number 2 as indicated in the layout information. So we have 3 other replicates to investigate the number of dual producing T cells and their presumed increased output of TNF-alpha. In replicate 1, the dual population is very similar in the number of counted spots, and the spot volume increase of TNF-alpha is here 366%. In replicate 3, this increase is 482%, and in replicate 4, the increase is 418%. Thus, a rather impressive consistency among these 4 replicates of tetanus stimulation. Even though we're talking about the same donor PBMC, each well in FluoroSpot constitutes its own individual cell culture. Despite this, the number of dual producing T cells and their increased secretion of TNF-alpha is very consistent. In addition to the FluoroSpot data explained so far in this tutorial, we also offer the possibility of exporting all data recorded in one single well. You access this by going up here to the Export button. A menu appears with a number of available options, including the one called Well Data Excel. Turning the switch button on and then pressing the Export button generates an Excel file with every single spot recorded, going from 1 to 971. their individual coordinates, their spot classification, volume in each filter, size in each filter, and peak intensity in each filter. From here on, you can extract the individual spot data that you are interested in and plot it accordingly. Furthermore, the export menu in Well View allows you to extract well images in either JPEG or TIFF. The cool part is that this option retains any spot center indicators that you have turned on while performing the export. For example, if we export this well image with the 57 dual producing spots indicated, an exact copy of this is created by Mabtech Apex with the dual indicators right there in the TIFF image. It's the revenge of the nerds. Furthermore, you export exactly the perspective you see in Well View. Here, for example, we can go into 600%, switch to the interferon gamma filter only, increase the brightness a bit, and then hit export well image. A new TIFF file is generated that is a perfect match for our zoomed in spots. Pretty nice. Let's go back to plate view, resave the FluoroSpot plate, and go check out the saved plate folder. In general, things are very similar to the ELISpot structure shown earlier. We start off by first going into the Excel file. In the Spot Forming Unit tab, we provide you with all the subsets calculated in a drop-down menu. You don't have to calculate the single populations yourself. But let me again show you the modern way of working in Excel using pivot tables. Just go into the plate database, select all, and insert a pivot. Just like in the ELISpot section, we use replicate number for columns and stimuli for rows. For values, I again here select spot forming units and change it to sum. Due to the nature of our FluoroSpot data, I must now add a filter into my pivot table in order to make sense of the data, and here our analyte names have been nicely exported into this category called analyte secreting population. I now go into the filter, select the dual population of interferon gamma TNF, and here is my data, nicely aligned in quadruplicates. It's a FluoroSpot dream come true. Let's go back to the saved folder again. Inside of the JPEG well subfolder, we have all the images saved, including all the overlays. You select in Preferences if you want to save these or not, in this way controlling the number of JPEGs that are generated every time you save a plate. In the JPEG plate subfolder, we have 5 separate images, one for every population, including the total ones. And finally, in presets, we naturally have 2 JPEGs for this dual FluoroSpot plate. I now want to talk about some other cool features. First off, pressing the Export button in Plate View brings up a menu that is slightly different than the one we saw in Well View. Here, one very powerful option is this one called All Open Plates Excel. With this functionality, you simply load in several ELISpot or FluoroSpot plates into the software, activate this function, and you get one single database exported into Excel. If all of them have added layout information like you've been shown in this video, you can then process an entire study from just one single powerful pivot table. It is the one Excel to rule them all. Furthermore, we have a comparison function built into Apex. You select the wells you want to compare, right-click and select New Comparison. Turn on spot numbers and highlight the spot centers. You can then export this into TIFF or a JPEG file. We end this tutorial by going into the Preferences section. Thankfully, it is rather small and easy to go through. First off, we have the Preset section. Here you're able to create permanent presets of your particular user, either by creating it from scratch or by nominating an already existing preset. User presets can be created for each filter available in Iris, including the white LED used in ELISpot. If we now go to the Reader tab, we here find exposure time settings for each ELISpot plate type and for each filter in FluoroSpot. Right now, the settings are configured to override the machine defaults, but by unchecking these boxes, the exposure value is fetched from a small memory chip inside of each Iris machine. These defaults have been calibrated by Mabtech and should work great for an absolute majority of readings. Way down we have something called Perform Center Detection, an algorithm which during reading looks for the border of the well, making sure that the AOI is placed correctly. ELISpot count and FluoroSpot count will not be available for any customers. These are Mabtech admin tabs where we set parameters for the raw spot algorithm. These will not show up in your software. Furthest to the right we have the Save tab, where you can control which files should be generated upon saving of the plate. In the bottom, we have an option for saving well JPEGs. Right now, the single filters only checkbox for FluoroSpot is left unchecked. This means that when you save a FluoroSpot plate, all well images are created, including the digital overlays. In a situation of a 4-color FluoroSpot, this would result in the generation of 1824 JPEGs if all 96 wells were saved. This can take a while. As a result, we provide the option of only saving the single filters, bringing down the number of JPEGs to 384. Alternatively, you can turn off the well JPEG generation completely by the tick box right here. This concludes our first YouTube introduction to Mabtech Iris. I hope this technical tutorial has been interesting to watch and that it has given you a lot to consider. For more information, please contact us directly at mabtech.com. We look forward to any type of feedback. Thank you and goodbye.